Connecting a raw, probabilistic language model directly to a middle school classroom introduces unacceptable legal and psychological liabilities. When a student asks a sensitive or dangerous question, an unconstrained AI might attempt to answer it playfully or inaccurately. In a highly regulated educational environment, that is a catastrophic compliance violation. Large language models are inherently probabilistic text generators. They compute the next most likely token. But school safety protocols, data privacy laws, and strict curriculums demand absolute deterministic guarantees. You cannot prompt engineer your way to strict compliance. Securing an AI in production requires building a rigid architectural routing system around the model itself. This is the operational philosophy behind the Socratic learning ecosystem, or SLE. Its entire architecture is governed by one unyielding rule: ontology over rules over LLM. The curriculum database dictates what is factually true. The rule engine determines exactly which pedagogical phase the student is in. The language model is completely subservient to both of them, permitted only to construct sentences within that predefined box. This illustrates a sandwich pipeline. The LLM sits isolated at layer 3 within a 10-layer stack, insulated by pre-flight classifiers above and post-flight validators below. To understand this density, we trace a high-risk student message from the millisecond they hit send. Forcing a probabilistic generator to behave in a deterministic environment requires physically stripping the AI of its decision-making authority. A standard microservice architecture splits logic across separate network nodes, but pushing a single text prompt through 10 independent validation layers over a network introduces crippling latency. To solve this, the backend operates as an in-process monolith. The main API service imports every security and logic layer as a local library, executing the entire 10-step gauntlet synchronously in a single process. The student's message immediately hits layer 7, inbound safety, splitting into a content filter and a strict notification classifier. If the text triggers the classifier for acute distress or peer bullying, the system instantly executes a hard detour. The pipeline halts. The external AI providers are never called. Instead, the system locks into a safety protocol, delivering a static, pre-approved response to the student while silently routing an escalation alert to the teacher. The most reliable method for managing an AI during a psychological crisis is to disconnect the AI from the loop entirely. If the inbound safety check clears, the message drops to layer 1. A lexical scrubber strips out personally identifiable information, ensuring student names and locations never leave the local environment. The sanitized text then moves to layer 2, where the system prepares to construct the actual instructions for the AI. In this architecture, prompts are not loose strings of code. They are strict, version-controlled YAML files stored in a dedicated package directory. Before a template loads into memory, the system calculates its SHA-256 hash to perfectly match a verified signature. If a single character has been altered, the hash fails, and the system instantly rejects the file, blocking execution. Treating prompt instructions as cryptographic artifacts ensures that no unauthorized directives can be injected into the deployment pipeline. The validated prompt finally reaches layer 3. Out of all 10 steps in this pipeline, this is the single permitted external network call. The system attempts to contact its Tier 1 provider. But external AI APIs are prone to rate limits, timeouts, and sudden degradation. If the Tier 1 provider fails within the latency budget, the packet automatically reroutes to Tier 2. If Tier 2 also fails, the system drops into the Tier 3 vault, pulling a hard-coded Socratic response from a local cache. This routing layer also enforces strict geographical constraints. If a school requires local processing, Layer 3 physically locks the request to regional servers, bypassing international providers entirely. A secure production architecture treats the language model as a highly volatile dependency, requiring structural contingencies to maintain uptime. The language model successfully generates a text draft, but under the rules of this system, that raw text is never immediately delivered to the student. The draft drops into Layer 4, the lexical guard, which scans the output against a massive regex blacklist of restricted terminology. Because of Turkish morphology, the word dokunma can function as both a dangerous physical action and a standard laboratory safety instruction. Simple route matching algorithms trigger false positives and break the conversation. The text then faces Layer 5, the semantic guard. Using natural language inference, this node mathematically verifies that the AI hasn't accidentally leaked the direct answer to the student. Layer 6 queries the curriculum database, cross-referencing the AI's statements against the established lesson ontology. This ensures the model hasn't hallucinated a concept or reinforced a known student misconception. This post-flight validation gauntlet treats the AI's generated draft with the exact same strict parsing applied to malicious user input. If layers 4, 5, or 6 detect a violation, whether a leaked answer or a curriculum hallucination, the pipeline triggers a regenerate protocol. As this loop illustrates, the system discards the bad draft and routes the packet all the way back up to layer 3, forcing the AI to generate a completely new response. This cycle repeats up to a hard-coded limit. If the regenerate budget is exhausted, the system determines the AI cannot safely answer the prompt. It aborts generation and defaults to the Tier 3 static response. A draft that survives the validators finally hits the outbound Layer 7 classifier, providing an independent verification that the model itself did not output distressing text. System alignment is achieved by physically trapping the large language model inside an inescapable loop of deterministic rules. The finalized payload is ready for the user, but milliseconds before it leaves the server, it hits Layer 8 for auditing. Layer 8 creates an immutable, append-only ledger. It assigns a unique SHA-256 hash to the current interaction, permanently linking to the previous turn. This metadata block records specific safety rule versions. During an audit, engineers mathematically prove why an output was authorized. But this intricate pipeline relies entirely on deployment execution. If the underlying database state isn't initialized perfectly, the entire backend enters a crash loop. The operational sequence is strictly enforced. The database schema migrations and the curriculum data seed script must successfully complete before the main API service boots. If a database seed fails silently, the AI boots with an empty ontology. It has no curriculum to anchor its facts, proving that rigorous DevOps orchestration is a strict requirement for AI safety. 10 layers of security, cryptographic hashing, and automated fallback loops, all executing sequentially just to safely process a single turn of conversation. Application architectures that rely on optimistic prompt engineering and disjointed microservices predictably fracture when subjected to the demands of high-stakes environments. The system functions because it obeys one rigid hierarchy. The ontology establishes truth, the rules dictate behavior, and the AI fills in blanks. Engineering AI in production is not about finding the perfect sequence of prompt instructions. It is about building an impenetrable, deterministic bounding box around a probabilistic core.